I'm starting a new lecture course. The title is going to be very much aligned with the title of the school. It's on integrable and chaotic systems, and in particular, I will discuss. Oops, too strong. Exactly. Solvable quantum circuits. So I will cover both integrable and chaotic paradigm of quantum circuits, but the topic is actually quantum circuits, which are, as I understand, probably not, at least yesterday they were not, I don't think even mentioned. So, if you look for similar buzzwords, you can also think of spin chains, but they're spin chains with some particular time evolution, which is manifested in terms of, if you want, a quantum protocol, discrete digital quantum protocol, which is these days called a quantum circuit. So it's a kind of modern word, but for me it's just, as you will see what it is. For those, most of you have seen that, but for those who haven't, for me this is just like a very simple toy model to study quantum many-body dynamics, right? We all like simple toy models, right? And to me these are kind of the simplest, the minimal toy models of studying many-body quantum dynamics of qubits. Or qubits, so models with finite dimensional local Hilbert space. So these are not field theories, these are not continuous variable systems, which are much harder to analyze. These are the simplest possible systems you can find in nature or in your whatever computer if you want, and you can simulate them. You can solve them sometimes. You can find examples of interesting paradigms in dynamics and in chaos. Or integrability. So my lectures there will be 4 lectures. There will be 2 lectures basically on the first part, and there will be 2 lectures on the second part. So the first part I will discuss, today will be part 1. Today I have 2 lectures, so probably I'll cover, I surely will cover the first part. Maybe I will already start a little bit with the second part. But the first part will be on integrable circuits. So, but before doing that, before starting that, let me just make a footnote. I don't know where can I make a footnote. Maybe below here I can make a footnote on notation. Oh, maybe I can just take a full thing and I make a footnote on what I will call tensor network notation. In this business, it turns out if you study integrability of spin chains, right, this is a subject which exists at least since 1970s. It was pioneered by a Russian school led by, so-called Leningrad school led by Ludwig Faddeev. So they produced a lot of spectacular papers with very fundamental discoveries, but they are very, very hard to read. I remember when I was trying to struggle with these papers, it was impossible, impenetrable, or whatever you want to call it. It was very hard. So I think, this is very algebraic subject. There is lots of algebra, lots of abstract algebra, and it's hard to really connect to physics, right? So to me, a revelation was when I discovered, people in quantum information started to use tensor network notation somewhere around, mid-2000, 2004, 2005. And this, I think, is a very, very, very handy tool, and it allows you to use diagrams instead of algebra, right? So, so for most of my talk, I try to use diagrams and try to write identities in terms of diagrams and proofs in terms of diagrams. So I try to convince you this is useful. And for those, most of you, of course, have seen, if you are working on related subjects, you have seen these tensor networks. But for those who haven't, let me just make a very kind of brief intro into this notation, but as you will see, I will use this notation, I will introduce notation as I go along, and you probably get used to it, even though maybe the beginning will be a bit unclear. But okay, let me just think of this, I mean, like I will have tensor. Tensor for me is a beast which has a couple of legs, and number of legs is number of indices. So for example, this would be a tensor A, which have 3 indices. Let's call them I, J, and K. So let's say something like that, or maybe we can put index K above. I don't know. We don't really care about lower and upper indices. I mean, anyway, we'll use diagrams, not formulas for most of the stuff, right? But that just to give you notation. So this would be like a tensor, right? And now I write sometimes a combination of two tensors like this, A and B, right? And what is it? This is just a very kind of particular type of matrix multiplication, meaning that I have here an index I, here I have an index J, here I have K and L, and here I have maybe an intermediate index M, which I sum over. So all the connected indices. So you can think of this as a graph, or, well, not really a graph because there are dangling ends. But you know, there are vertices, which are called tensors, and then there are lines between vertices, and the lines which connect to vertices are summed over. They're always summed over. So this is just another way of writing a formula, which would be A, K, I, M, B, L, M, J. Okay? And this is what you will see. This is actually useful, right? Because we will often have this type of matrices which have two lower indices, which correspond to row and the column, and an upper index which sticks out, which corresponds to something else. And when you multiply these two matrices, you get an object which has two out indices. And you multiply 3, you have 3 out indices. And in this way, you construct many body wave functions in this type of physics, right? So this is a very useful way of constructing many body wave function, which can be highly correlated. And the correlation is encoded in this auxiliary index, which is summed over. Okay, so I mean, people who have seen what people who do DMRG or MPS-based methods, I mean, this is their bread and butter. Yeah? For me, this is not bread and butter, but it is not just a notation. I mean, okay, I mean, I will use it, but not for doing numerics. I will use it to construct, exact expressions. Please ask your questions at any point, any time, anything which might be unclear. So, yeah. So anyway, and then, so what else can I say? I mean, like a simple vector for me would be this, right? This would be a simple vector, which has one index, right? If you call it VI, right? And then a matrix time vector multiplication would be like, this would be a matrix, A, and I apply to vector, and this would be again a vector, right? Or something like that, right? Just to get comfortable with notation, right? Okay. Right, so now this was just a footnote. Now I go directly to what I call integrable circuits. So now let's try to define a class of circuits which we might, or one might call them integrable. And well, you'll see what I mean. Integrable is of course a very well-defined word in this field. So we'll have been integrable because it will be related to Young-Baxter or Bethe-Ansatz or this type of things. Okay, so now let's define a fundamental concept. Let's define a QDIT. QDIT for me is a Hilbert space, which I will call a local Hilbert space. I denote it as H1, and this is just a d-dimensional space. That's why it's called QDIT. For all examples, this will be qubits, so d will be equal to 2. And this is kind of the standard bit, the standard quantum of quantum information that people use when they try to abstractly encode many body states into quantum computers, right? I mean, this is the smallest unit you can have. Right, but of course, one qubit or qubit doesn't do anything interesting. Of course, you have to have several. For example, let's take 2. Let's take 2, and let's take a gate. Let's take a unitary operation, which will be some map over tensor product of 2 of these guys, right? So this is just notation, means space of all matrices, all linear maps over this vector space, right? So So what we'll have, of course, I will try to be very gentle on the algebra, and I'll try to just replace everything with the diagram. So let's immediately introduce a picture for that. So what we'll have now is a little box, and we place a symbol which this denotes, well, this element. And now there are, well, I mean, this is what is it? I mean, this is an object which is a matrix, which means it has the in indices and has an out indices. Let's just, for the time being, put some arrows just to stress that these are, I mean, later I will skip arrows. It will not be unambiguous. But let me just, for the moment, put some arrows. So now this will be ij, and this will be kl. Okay? So that's a matrix which I will denote as, which I could write as ijkl. Endomorphisms. It's a space of endomorphisms. Yeah? It's just a notation for space of all matrices over vector space, or all linear operators of the vector space. It's a finite, everything is finite dimensional, no worries, I mean, this is completely elementary linear algebra. Yeah? Okay. So now, what is this, right? I mean, now I'm just, using some more familiar notation, which is, I claim, much harder to use, but still it's much more familiar. So I could write this u as a sum over ij. This will be Dirac notation, right? Dirac will say, okay, this is a linear operator, so how can I write it? I can write it like this. It maps state ij of 2 qubits to kl, okay? And this is the amplitude for that, right? So this is an operator, right? Okay, or if you want, operator is completely specified by its action on any basis state. Basis states can be labeled by products of, single qubit states, ij. So then it's just the sum over kl, u, ij, kl, kl. Okay, right. Maybe I can, because this is kind of sticking out, I can erase that, right? So that where is the, I'm not sure if the wet eraser would be perfect, but let's see. Okay, so now, So now what can we say about these matrices? They are unitary, so what that means? It means you can write another matrix, which we call U dagger. I'll put a cross here. This will be U dagger, right? So this will be U dagger, which means ij to kl, which is the same as u kl ij star, or let's call star, complex conjugate, right? And now what we know is it's key property of unitary, of gates, or of dynamical maps or whatever. Manipulating quantum states is unitarity. So you should preserve, right? You should preserve whatever, norm and inner product. So unitarity of this gate can now be simply written as this tensor diagram. You have U here, you have U dagger here, and that should be equal to this. Okay? Because when you sum over, this is now just, you have this object, which is a composite object. It contains two qubits, but still it is unitary, and the unitarity is just this, right? When you compose this object with its Hermitian conjugate, you get identity, and this is identity, right? So if you think, let me just still write, later, of course, I will not write all the names of the indices, but now let me just still do it. Let's call it this I prime, J prime, and this intermediate indices K and L. And now this would be I prime, J prime, and this would be just delta I prime, delta J prime, right? Because these wires require that this should be the same as this, right? So I should be the same as I prime. So just an open line thrown at the board is the identity, right? Because the two ends of the line should match. So this is a Kronecker delta or unit matrix, right? Good. Now we are ready to do something more sophisticated. Let's define what we call a brickwork circuit. So that for me is already kind of something very, very neat. It represents many-body dynamics in a kind of homogeneous way. I mean, and it represents local interactions. Why is that? Well, let's see how we want to define that. So now we'll take a string of qubits. Let's take a string of qubits. String of, let's say L qubits, and define this as a vector space, which we'll denote as HL, which will be tensor product of H1. For 2 qubits, we had a just top product of the 2. Now it's a tensor product of L of them, right? And now define a piece of or unitary, which I will call a U even with the subscript E. U even will be just a tensor product of L over 2. So L should be even for me to make life simple. If L is odd, we can also cook up something, but we have to discuss separately. So let's think of L being even. So let's take, because U acts on 2 sides, let's take L over 2 copies of U and place them one next to another. So what we do now, what is a tensor product? Tensor product is just writing pictures. I mean, in terms of diagrams, tensor product is just writing 2 pictures next to one another and interpret them as a bigger object, right? So now, and I mean, yeah, of course, there's something which I have to say, because it doesn't agree with 100% of the literature. For me, time is, well, I mean, but as I understand here, mainly there are people who are more interested to high energy than to condensed matter. So in high energy, I think it's totally common, but maybe not in all fields. I mean, I use the time which goes vertically, right? So for me, everything acts on something at the bottom and produces something on the top, right? So for me, all the operations are vertical, right? Like if you read quantum computation, literature is the opposite, right? I mean, engineers like the other notation, that things go from left to right. I mean, just to make sure that we are following. Right, so what would be now this tensor product? This tensor product would be L over 2 boxes like that. And then I will just put lines in and out. Yeah. And again, I mean, you can ask me, why do I write these lines as a skewed, not vertically, because actually they act vertically, right? So, I mean, again, being kind of more standard, I would maybe write these lines vertically, and I could, nothing would be different, but still I prefer to write them under somehow 40-degree angle, because in this way I stress kind of symmetry between space and time. I mean, there will be symmetry between space and time, which will be important for quantum chaos of my last 2 lectures. And we'll see that symmetry between space and time allows us to solve some chaotic quantum circuits. And that symmetry, even though time and space for me is completely discrete, I mean, it's still kind of, yeah, it smells a little bit of kind of covariance or Lorentz invariance or whatever. And we can discuss it on Thursday in my last lecture. Anyway, so now what we have now is basically, well, indices, which, let me now just write Roman numerals. 1, 2, L minus 1, L. I have L indices, and now they go to 1 prime, 2 prime, 3 prime, and so on to L minus, so like that. Okay? So now this to me is U even. It's a picture of U even. Nothing very interesting yet, right? Because these are just like, I mean, this is, of course, it's a many-body map. It maps on a many-body Hilbert space. By the way, the dimension of this Hilbert space, just not to forget that we are dealing with non-trivial objects, the dimension of this Hilbert space is d to the L, right? Dimensions of spaces, when you do tensor multiplication, are growing as products of dimension of factors, right? So L factors means d to the L. So it's huge, and it quickly grows over the number of atoms in the universe. But it's still kind of trivial because it only couples 2 neighbors and doesn't do any other coupling, right? I mean, so if you iterate this, it just sits separately in the boxes which contain only 2 qubits. So now let's to make something non-trivial, we have to do two more things. We'll make a shift. We'll define a shift map. So now try to be a bit. Shift map again is a unitary, which I'll denote as pi. Again is, and it's completely specified by its action on a basis or product states. So So take a product state. And shift map, just make periodic shift. Okay. So it just rotates by one side. And then I will take another element, which I will call u odd, which will be a conjugation of u even by a shift. It doesn't really matter where I put the inverse. So whether I conjugate left or right, I mean whether I shift it left or right, it doesn't matter, because for me, also one thing I would have to stress at some point, I am, for the purpose of these lectures, to make life simple, interested in homogeneous systems, in systems which are translation invariant. So all my u's are equal. Yeah. I could actually, well, actually that's not completely true. I mean, on the last 1 or 2 lectures when I will discuss quantum chaos, I will have to introduce some disorder at some point, but maybe at the very last point. Before, I will only consider homogeneous systems. So what happens now? Well, now I would have to, if you allow me to make a little bit of erasure here, just to, I would probably, it would be much nicer for me to use the same picture. So let me just erase that for a moment. To make space here. And now I will make a picture for u odd. What is u odd? Well, it's just shifted by 1, right? So put one box here, one box here, and then, well, whatever. Now, of course, everything. Now I have periodic boundary conditions, so I have to make half a box on the left and half a box on the right. I don't know if I want to do that. Do I? Maybe not. Maybe I'll just put a box like this. And so what do we do now? Well, we do now like this. Now already, well, before I would connect these lines, let me not connect them for a second. Before I would connect these lines, I would call this u odd, right? So this will be u even. This will be u odd, right? And well, let's see what, I have to now bring this guy. This guy has to be connected here, right? So now this is connected here. I will just make a little hook to denote that this point is equal to this point, right? Because everything is on a circle, right? So this is the first bit, which is connected to the last bit here. Okay, so now this is u odd. And then we go back. Now this guy then comes back. Okay? And now this is, well, now I connect the two things. I multiply. So now I define u as product of u, well, let's start with u even, and then first u even, and then u odd. So what is the product? Now again, I showed you earlier how to multiply operators. Now I multiply these composite operators. But everything is completely clear, right? Once I have nice notation, I just have to connect the lines, right? So I get this. Okay, now maybe it's better to not to have things dangling in the air. So let me just write another picture with exactly four boxes. So now L is equal to 4. Now we have 1, 2, 3, up to 8 here. And now I have, well, now this guy goes on the other side, comes back here. And this one was connected to this guy here. Okay? Now I hope you imagine how this works, right? So now I got a final state after one iteration, which is this one. Okay. So now this is all very, very easy, very straightforward. I hope there is nothing ambiguous about what I did. You make kind of two huge matrices of dimension d to the L. You multiply them, you get another matrix of size d to the L, but this one now is non-trivially coupling, right? This one is really, encoding information, encoding strong coupling between qubits, but in a way which is completely local. Which means that this guy, after application of this, you see now you see how the information flows. What can be coupled to what, right? If you start by this qubit can, in one iteration, only be coupled by a tree of qubits which go this way. So which means this qubit can only, the state stored in this qubit can only affect states of these 4 qubits or qubits after one iteration of the map. And then I do another iteration of the map and I get another +4 qubits which are coupled, and then another +4, another +4. So this is the way information propagates in this type of brickwork. Okay, now you can easily think of, since I'm doing a Blackboard talk, I cannot write to, I don't want to mess with the computer slides, but you can easily imagine now to make a large network of this type of gates, and then you see that you get basically a light cone which opens at speed 1. So there was someone, there were several mentions of Lieb-Robinson theorem yesterday, which is a great theorem about Hamiltonians of quantum spin chains of finite quantum systems coupled locally with Hamiltonians. And that theorem tells you that there is some sort of effective speed with which information can propagate after you do time evolution via e to the minus ht. Now we do an abstract toy version of that. We are not doing this, we are just doing this u to the t. That u. Now we have this u, right? This is the u, which is a composition of u even times u odd, or u odd times u even. And once you power it, right, it's like, this is one fundamental unit for us, and now you power it, and then you get time evolution in discrete time. Now time will be discrete, like the space is discrete, and the iterations of this map will be giving us time evolution for increasingly long times. But I want you to appreciate this fundamental fact that this is just a caricature of this type of dynamics. And here, light cone is for free. Lieb-Robinson is for free. There is nothing to prove. Well, if you are a picky mathematician, maybe you want to prove something, but for a physicist, it should be completely obvious, right, what's going on. Why do I say that everything depends just on these qubits? For example, apply this to a separable state product of qubits, right? Everything outside the light cone remains in the same product after t iteration of this map. Everything away by plus minus t from the initial whatever disturbance. You make a disturbance, you make a quench. We take a initial state which is invariant and let's say trivial initial state, right? Try to say too many things at once, but I guess it's clear what I want to say. So if it's not, please do ask or bug me later in the question time. Anyway, so right. Now, good. Now what, for those who found this still too abstract, let me make some example. Yeah. Let me make some example. Example is just what perfect example for what I've constructed is just, standard picture of spin Hamiltonians with local interactions. So example is the so-called trotterization of local Hamiltonians. How does it work there? Well, you imagine you have a Hamiltonian which has an interaction which couples two sides. Now, when I will often use this notation when you should bear with me because when I write explicitly matrices, then indices mean states, right? Which these matrices, the operators act on. But if I think of many body operators and I put indices like that, then this also means the states. The sides in this tensor product space on which this operator acts non-trivially, right? So this would be like, now imagine that again, L plus 1 is equal to 1, so periodic boundary conditions. That would be a Hamiltonian of a periodic locally coupled system. And right, so then H12 is only coupling two sides, okay? Well, again, I'm a bit nervous now, right? I mean, you see this is not precise what I wrote, because this is embedding of a two-side Hamiltonian into many-body Hilbert space. So it's not quite correct. It is still many-body Hilbert space, but you know, J plus 1 can be thought of as shifted. Well, I should do something different here. Sorry. I take 1, 2, and I shift it, let's say, by x minus x. X is some integer. Then I have h, x plus 1, x plus 2. So this is a local Hamiltonian. And then, for example, just to make life very concrete, take a Heisenberg Hamiltonian, for example. I mean, this is something that I will actually use a lot later. Okay, well, this, you can think of this, you can write it in terms of Pauli matrices, so sigma 1 x, sigma 2 x plus sigma 1 y, sigma 2 y, plus let's call it delta here, sigma 1 z, sigma 2 z. So this would be like an XXZ model, anisotropic Heisenberg. Delta equal to 1 will be called XXX model. So I hope you all see this. You have all seen this kind of nomenclature. If not, this is the definition. These are very, very, very popular toy models of quantum spin chains. They are, by the way, also integrable, and I will discuss circuit versions of these models in the next, let's say, part of the lecture. So now, let's start with the Hamiltonian version. So let's think of a local Hamiltonian, whatever this local Hamiltonian density is, but for concreteness, we can imagine this is just a Heisenberg Hamiltonian. And then, right, and then you can think of, you use Trotter formula, and you can say, okay, for a short enough time, this is equal to product of U odd, U even for small time. And then whatever u to the I, whatever, tau. So for not small time, you can write otherwise. For not small time, you can write an expression which will be e to the minus I tau over m h even, h odd to power m, like this, to the minus I tau over m h even, then to power m. And now this you can now treat of as u odd and this as u even. So what I want to say is, of course, if time is not short, you can split the time into m pieces such that tau over m is short, then you apply Trotter formula. And each of these little pieces now is a quantum gate, right? Because now what is h odd, h even is just a product of, sum over even sides. Let's write it like this, j minus 1j, that it will fit my notation, and h odd is sum over odd sides, hj minus 1j. Or, yeah. So now you see that our gate is just e to the minus I tau h12. I mean, this is now sum of commuting terms, right? HO contains commuting terms. So the exponent of sum of commuting terms is product of exponents. And this product of exponents is a product of gates. Okay. Okay, now this is, I think, should be completely obvious. But now let me do something which is maybe less obvious, is now introduce integrability into this business. Okay, so now this was notation. So this was, let's call it 1b, Young-Baxter. Integrable circuits. All right. Right. Let me just start with an example. Take the following gate. Take the following, let's say, d square by d square matrix. U of tau, put tau as a formal parameter, write 1 plus I tau times p divided by 1 plus I tau, where p is a permutation. P is a permutation or swap. Sometimes people call, in jargon, they call it swap gate. So it just flips, right, the two spaces. It's a unitary which flips the two spaces. Now for d equal to 2, I can write this as a 4 by 4 matrix completely explicitly. 1, A, B, B, A, 1. There are 6 non-zero elements, and all the other 10 elements are 0. And A is equal to 1 plus I tau, and B is equal to I tau divided by 1 plus I tau. So if tau is real, this matrix is unitary. It's very easy to prove that, right? You just take U dagger. What is U dagger? U dagger is this P is self-adjoint, right? So U dagger is just the same expression with tau going to minus tau. Then you apply U and U dagger. Then you use the fact that P squared is identity. And you see that what you get is identity, right? It's a trivial exercise. So this is a unitary matrix, great, for any tau. And for our case, this matrix, actually, this is a very interesting model, and this is sometimes called a 6-vertex model. Well, it is always called 6-vertex model, but in this context, it's a bit surprising. I mean, surprising. It's a bit unusual application of 6-vertex model, right? People who study 6-vertex model, for example, when they compute entropy of ice or things like that, I mean, 6-vertex model is a model of statistical equilibrium, statistical mechanics, and there usually the weights are positive. Now for us, this is again algebraically the same model, but the weights are complex. A, B are complex numbers, and the matrix is not, well, it's not a matrix of Boltzmann weights, but it's a unitary matrix. So we'll just use kind of integrability in ordinary stat mech, but the object will be unitary rather than positive. Okay, right. So now, I don't know if you have ever seen that, but if you look at the Heisenberg model, where delta is equal to 1, then this object is actually related to permutation, or to the swap, right? It is up to a constant equal to a swap. So we can also think of it as a Trotter limit. In Trotter limit, this goes to a Hamiltonian, which is just sum of permutation. So this can be sort of as a, for small tau, this can be sort of also as exponential of e to the I tau, e to the I tau p, right? It's just another way of writing exponential, right? It's a basically spanning exponential to first order and correcting for the norm by dividing with something close to 1. Okay, right. What's special about this model? Well, I mean, this model, what is really special is that it satisfies a very interesting relation, which is called Yang-Baxter relation. Or directly for the object U, this relation is called the Breit equation. Or sometimes they call it the Breit form of Yang-Baxter equation. So what is this equation? Well, you think of these U's now to act on 3 spaces. I mean, you think of a triple of U's, which act on 3 different spaces. So I will again denote the number of the spaces on which this acts non-trivially. You take, for example, U1, 2 of parameter mu. Then you take U2, 3 of parameter mu plus lambda. And then U1, 2 again, parameter lambda. And that should be the same as U2, 3 of parameter tau u1, 2, parameter mu plus tau, and parameter u23, u23, sorry, now I switched between tau and lambda. Sorry, it should be tau, then this tau mu, and then this mu here. Okay, so there are two parameters, mu and tau, which are completely arbitrary, and then there is the sum of the two. And there is, well, this is one way of, and of course you can prove this equation. It's again, I could give it as an exercise. But before doing it brutally, maybe we can rewrite it in a nicer and even more elegant way. We can write this u as permutation times what is called an R matrix. Again, everything is a function of some parameter, which later people call it spectral parameter, or we call it a spectral parameter. So this parameter is sometimes a free parameter, sometimes is fixed by the parameter of the model. So for us, we started by a model for which this parameter has a fixed value tau, which defines a particular circuit. But then we'll introduce a different, various other manifestations of these operators at different values of spectral parameter, which will be free. So because of these kind of nice identities, we'll actually be able to have some free parameters, free spectral parameters in the game. And this will be important because this will allow us to construct infinity of conserved charges of these type of models. And again, I mean, for those who have seen how the integrability works, there is nothing new in this. But it's very nice to do it directly for the circuits without having to resort to Trotter limit and to Hamiltonians. As you will see, I mean, people, when they construct integrable models, they want to cook up R matrices such that logarithmic derivative of transfer matrix then is some local Hamiltonian. For us, there is no need to have a local Hamiltonian from the start. We just want to have a local gate. And a local gate for us will be just related to an R matrix, as you will see. So we just start from any solution of the Young-Baxter equation. Suppose it's unitary, and then we can have a integrable circuit. Okay, now let me just, for those who have not enough mileage in this, let me just tell you another thing, which is kind of very intuitive and allows you to prove these things really in an intuitive way. So you can write this gate as, this is just a redefinition of whatever, our definition of this object P, because P squared is 1 anyway. So you can write an object which is called an R matrix. An R matrix is something like a scattering operator. So we can now think of this as an identity for the following diagram. We start with this diagram, and then we put particles or qubits into lines of this diagram. And then this go like this now. And now this should be equal to a diagram which is the same as here, just these lines are like in Mikado, it can be shifted a little bit, but the outer lines should not change really. Only the inner structure of, you can think of this, of course, time goes vertically. You can think of this as a 3-particle scattering, right? There are 3 particles, first 1 and 2 scatter, then 1 and 3 scatter, and then 2 and 3 scatter. And here is the other order, right? 1, 2, 3, 1 prime, 2 prime, 3 prime, 2, 3 scatter, 1, 3 scatter, and so on. So of course, now this is just the Young-Baxter equation, and even more. You can think of now having these particles to have some momenta. Let's call them lambda 1, lambda 2, lambda 3, lambda 1, lambda 2, lambda 3. And the object that acts, the scattering matrix that acts when 2 particles scatter, it depends only on the relative momentum, on the difference of 2 momenta. That's, let's say, the simplest possible situation. And this object then is when 2 particles meet, 1 and 2, then this object is just R matrix, which depends on difference of momenta of 2 particles, okay? And then this equation, of course, is equivalent to what I will call, what you can write now as I said already. You look at this diagram first. Which one? This? Okay, I start from the right diagram. No, from the left diagram, but I have to start writing from the right. So R12, let's call it tau now. I will explain what I mean. R13, tau plus mu. R23, mu. That should be equal to, and now this is 1, 2. This is the left diagram, right? Yeah, start 1, 2, and then 1, 3, and then 2, 3, and then the right diagram would be starting 2, 3. Okay, let me just write the symbols and then I'll explain. I mean the spectral parameters are 1, 3, mu plus tau, and R 1, 2 of tau, and then tau is lambda 1 minus lambda 2. Mu is lambda 3 minus lambda 2, and then if you add them up, mu plus tau, you add this up, lambda 2 cancels, it's lambda 3 minus lambda 1. So that's relative momentum between 1 and 3, this is between 2 and 3, and this is between 1 and 2. Sorry, now there is some problem, this should be 2, 1, yeah. Like this. Okay, and then everything is consistent with what I've said, so, right, and okay, I mean, this is just another way of writing the same equation. Of course, proving this equation is, I mean, it's just, actually this equation is satisfied for the two extreme cases, for the identity, for unit operator and for the permutation operator. And then, so this already gives you the, I mean, everything is like a polynomial in spectral parameters, right? So you can just check it term by term that it holds. And the two extreme terms are trivially satisfied, and then the rest is trivial checkup. Anyway, so now let me out of this define, okay, so now this, well, right, so now, okay. Okay, so now, of course, I promised you that I will not use much formulas, I will use diagrams. So let me just now forget about these tedious formulas and try to write diagrams. Of course, okay, already one diagram is here, which is often used, which is the Young-Baxter equation, but I will have to now have diagrams which are directly applicable to simplifying circuits. Okay, so now, now let me try to write a version of this equation which I just wrote here, which I will get when I will apply a permutation operator P12 on it. When I will do that, and then I will write a mu as lambda minus tau over 2. So lambda plus mu plus tau is lambda plus tau over 2. And to simplify notation, I will write this as lambda minus and this as lambda plus. So this will be two kind of, useful parameters for me. Lambda will be a free parameter, tau will be a parameter of the model, and and then will be basically compact notation, lambda plus, lambda minus, which means shifted parameter. So let me try now to find this useful identity out of this equation by just applying P12 on it. So so now this is just some exercise in permutation group. When I apply it, right, you just have to permute indices. When I apply the permutation, so so for example, things like that, P12, R23 is just when this guy goes through, is like conjugating R23 with P12, which means flipping 2 and 1, which is R13, P12. Okay, this will be something that I will use, right? Okay, so let me just finish on this board by writing this equation. What do I get? What do I get? When I go through here, I take P12, then I get R13 of mu. So mu is, as I said, mu is lambda minus. P12, R13. I mean, P12 just goes through, right? I multiply from the left, it goes through. Once it goes through this guy, it touches 2 and it moves it to 1. This guy, it moves to 2, 3. And this is tau plus mu, which is lambda plus. And then it collides head-on on R12, but this it cannot get through anymore, but it's a definition of the gate. P times R12 is U12. Okay, this is the left-hand side, and the right-hand side is I collide with the gate immediately, so I get U12 of tau, R13 here it is lambda. Mu plus tau is, what is mu plus tau is lambda plus, and R23 mu is lambda minus. So this is the fundamental relation that we'll use. And basically that's essentially everything that we'll need is this relation. What does this relation do? Well, it basically tells you that if you apply the gate on the product of two R matrices, then what you get is basically just flipping the spectral parameters. You see this is R13, R23, 1, 3, 2, 3. Here it's lambda minus, lambda plus, and here is lambda plus, lambda minus. So just a flip of spectral parameters. Okay, that's the action of the gate. Okay, any question? So okay, now we did all the algebra, so now everything will be simple. So let me just first write a picture for this formula, right? So now let me write like diagrams, which will be useful. So again, for this little square, which I put tau inside, what I mean is just a gate, right, as usual. And then the R matrix, or the other matrix, which I will call well, an R matrix. You may also think of it as a Lax operator, but again, this model is so-called fundamental integrable model, so there is no difference. But typically, then we would have to have a Lax operator here. I mean, this is again, this equation needs maybe a little bit more mention, right? I mean, this is fundamental integrable model, so R is equal to L, which would be a Lax operator. And this is let's say, in some textbook on integrability, this relation is called R check LLL relation, right? Or it's a discrete time version. R check LLL relation is, well, it's the same, yeah. Why R check? R check is what, Fadeev school calls U, right? It's P times R. It's just a modified R matrix, which satisfies Braid equation. And these are the Lax operators. And this is like, when you apply R matrix to a product of Lax operators, you just intertwine spectral parameters. Yeah. So that's a general relation, which basically acts, a form of which exists for any integrable model, where in general you should put a Lax matrix instead of the R, right? But in this particular simple model, we get an object which is basically, we get a relation which is only using R matrix, nothing else. But it uses R matrix in two different forms, which I will denote differently, so that I could actually use the same diagrammatics for other integrable models. So this will be my notation for Lax operator. Why I use it like that? Because now I have an auxiliary and physical space. Here I have two physical spaces. So I'm trying to use oriented diagrams for which vertical direction is special. Horizontal directions are, but vertical is physics, horizontal is auxiliary, right? So now this is what I will denote as physical space before and after application, and this is what I will denote as auxiliary space. Well, now I wrote it. I write it with the numeral 3. Later, maybe I'll use the numerals like A. Again, you can write arrows here, just for once, so that you have an idea that these are operators which moved in. Here, this is an operator which applies on a product of physical and auxiliary space, and it spits out a state in a product of physical auxiliary space. And here the same. Okay, so now this will be R, and here I will put some number here, and this number will be usually lambda plus minus. So this will be R 1, 3, lambda plus minus. And now this strange, heavy equation now can be written in terms of some identity of two diagrams. Well, let's write the left-hand side and right-hand side of this equation. Left-hand side will be, or maybe start with the right-hand side. Right-hand side, sorry, just do the left-hand side if time goes bottom up. So this means we start with U12. with U12 of tau, right? And then we apply it to a string of 2 luxes. And the first one is, well, let's call it the one which is 1 is lambda minus. And here I have lambda plus. And this is equal to this guy, right? This is the right-hand side of the equation. We start with the product of R1, 2. I mean, acting on 1, 3, and 2, 3. If you want, I can still put some arrows now to make life completely straightforward. Right? So now this is different order, right? So now the right-hand side has the left one has lambda plus, the one which is in physical one is lambda plus, and here is lambda minus. Okay. So now this is the key identity. Basically, for the next 1.5 lectures, I'll be using repeatedly this identity. Index 3, let's see. Index 3, what do you mean? 3 is, why shouldn't,
it's the same one.
Yeah, why shouldn't be, yeah, it's the same. 3 is special. 3 will be, I mean, later I will put maybe letter A to denote that it's special, it's auxiliary. It need not be even the same space. I mean, for the time being, this is all C2 or CD, C to the D, right? But later on, we'll use representations of Young-Baxter solutions of Young-Baxter equation, which might not be uniform in all the 3 spaces. And so this could be a special space. And it's actually very useful to allow it to be a special space. Anyway, so now this is a, but now let's do, I mean, this is supposed to be completely simple and elementary. So I'm, yeah, I should probably close in, well, I started a couple of minutes late, right? So I can, yeah. So I will try to finish at least for the first main part, so to show you a transfer matrix and what we mean by integrability of this circuit. Okay, right, so now, now I'll make a claim. Now I'll make a bold claim, which will be trivial to prove, actually, or very easy to prove. Maybe I can, no. I can just write a claim here. The following transfer matrix it would be better to call it transfer operator, but nevertheless it's transfer matrix, well, according to most of the literature, T of lambda which has the following form. Again, bear with me for a second. I'll sketch you a diagram for that, which is much easier to swallow. But now I'll write it as a trace of A. And now this arrow says that J runs from left to right. So this is an ordered product of J running from left to right, from 1 to L over 2. It's a product of R, and now there is a odd indexed and auxiliary, lambda plus, and then there is the even indexed, comma auxiliary, lambda minus. And that's it. So that's sometimes referred to as a staggered transfer matrix, or diagonal to diagonal transfer matrix in the language of the usual 6-vertex model. It's a bit special, again, for those of you who have some mileage in integrability, but might still not seen this type of beats before. I mean, I warn you that this is a, usually you write product of Lax operators here, right, or just R operators, again, for fundamental integral models, but there is no distinction between even and odd. I mean, there is nothing special. Now, here we have we always have this kind of staggering, even and odd staggering, right? Because things are discrete, so the minimal model is still kind of staggered, right? It's not translation invariant with respect to shifts by one side, but it's translation invariant with respect to shifts by 2 sides. So we have to have this staggering built in. But of course, you'll see, I mean, immediately why this is important and how does this enter. Okay, so now this is the transfer matrix, and the claim is that this transfer matrix commutes with time evolution. Time evolution. What does it mean? It means that u of tau of lambda commutes for any complex spectral parameter. So this is what you usually mean by integrability, that there exists a rich family of operator-valued analytic functions, which are called transfer matrix, which commutes with time evolution. And this will be able to show, this will be a simple diagram. So if you allow me for 2 more minutes, I will just write a diagram so we can stare at it, maybe also during the break, and then I'll stop. And then you'll see, I need this upper because, yeah, otherwise I'll have to draw it again in the next lecture. But anyway, so maybe if I can take extra 2-3 minutes, I can draw it. So what is the proof? The proof of this is just writing pictures, right? Proof is writing picture, but I will assume now that L is equal to 8 for concreteness. So let me try u of tau of lambda. So if u of tau of lambda is what? We start with tau. We start with tau, with t of lambda, which has whatever 8. Yeah, it's still 2, 3, 4, 5, 6, 7, 8. And then we start with lambda plus, lambda minus, lambda plus, lambda minus, lambda plus, staggering, right? And then we take a trace, okay? Now for me, auxiliary space is already indicated by A. So this is the space A, which I trace over, okay? And this is an operator. It has indices 1, 2, up to L. And then I apply U on it. First, I start with U even, which is this guy. And then U odd. Right, and that's it. So now this is U even, this is U odd. Okay, this is the full U, which I apply on T of lambda. Okay, that's the diagram. Now just look at these pictures above. So now I have to replace this guy. Of course, if I had an iPad, now I could just erase and replace on the fly, right? But since I don't have the technology now, so you can imagine in your brain, right, what is happening. This diagram is just, this guy are pulled up, this guy is pulled down, and lambda plus and lambda minus are swapped. Again, the same, lambda plus minus, lambda minus are swapped. Now you look at, okay. Then you would have lambda plus, lambda minus here, right? And now you will use the same thing, right? And you will use lambda plus, lambda minus. So let me just give you another color picture. Maybe that's what I should do. Lambda plus, lambda minus here. And then I will do this again for here, and then I will get lambda minus. They are this. Sorry, yes. This is lambda plus, lambda minus, and then again here it's lambda minus, lambda plus. So you see, at the end of the day, you get exactly the same lambda minus at the same position as here, right? So that's the point. You take 2 half-time steps. One scrambles indices from even to odd, but another restores them back to even, yeah? Or even to even, odd to odd. Yeah? So after applying this sort of diagram twice on 2 layers of this guy, then we get that. Then we get the following, right? We get this ladder. 1, 2, 3, 4, 5, 6, 7, 8. Lambda minus, lambda plus, lambda minus, lambda plus, lambda minus, lambda plus, lambda minus, lambda plus, and then No, this is the no. Sorry, this was the one I used last. This is the one. Sorry. And so this is the final result, right? After two actions of this layered, two layers of this diagram, these identities, and this is just what? This is just starting with U and then finishing with T of lambda. So this works for any lambda, which means we proved commutativity for any lambda, right? And then, okay, now I have to stop. So you'll see what we do next. I mean, just make some couple of further steps, right? Out of this T of lambda, we can construct conserved charges. We can furthermore prove that these lambda are in involution, that they commute among themselves for different lambdas, and so on and so forth. And then we'll do other exciting things. So thank you for your attention.
There's an announcement. Sorry.